Okay, welcome to the third class meeting of EECE451, the introduction to signal processing. About the number of homework, I decided to just synchronize the number with the corresponding class meeting. So our homework started with homework number 2. Don't be confused. Okay, here goes the overview. As I told you, most of the first half is covered in some signal gen systems. So if your signal gen systems cover this part, just enjoy the around 1/3 of these class meetings. If you haven't, then you must study hard, okay? I'm kind of starting very slowly, but I will become faster and faster in covering the prerequisite part. Okay, here goes the review of last class meetings. The first one was the difference between analog signal and digital signal. No one can easily define what are these, but usually analog signals we believe are natural real-world signals. And digital signals, we just say that some bits are assigned in the signals. The problem is that in order to develop a mathematical theory, we cannot rely on very vague definitions. So we have very, very clear two definitions. One is the definition of continuous parameter signal. So X is a continuous parameter signal. For example, if F is a mapping rule from R into R. So the name of the signal X is used here, and here goes our parameter. Usually we use parentheses and T to denote it has the unit of time. Sometimes we have complex valued signal. So in that case, the continuous parameter signal is a function from R into C. Instead of using digital signal, it's hard to define. We use a definition. For example, X sub D is a discrete parameter signal if X sub D is a mapping rule from the set of all integers to the real numbers or the complex numbers. And we prefer using square bracket instead of parentheses for discrete parameter signals. When these time indices mean, these parameters mean time indices, then we prefer to call the signal as a continuous time signal and discrete time signal. Again, I leave the definition of digital signal away from this course because there is no consensus. But I would imply that a digital signal not only kind of quantized in the time domain, so it's a discrete parameter signal, but also it is quantized in the range. So the complex set is kind of converted to a discrete set or a countably infinite set, or sometimes a countable set if we assign a finite number of bits to each sample. Anyway, so this part will be a little bit less emphasized in this course. So the focus in this course is a discrete time signal. And as I told you, it's a function from Z into R or C. And we've seen the notation. And here comes two definitions. One is what is a graph of a function? You know. And what is an illustration of the graph? So given a discrete time signal, graph is a set of what? Set of n and xn, if you want. Here, sorry, x. Something like this. So it's simply the set of a pair. However, for illustration of this graph, there are many different ways, and most of the cases, the textbooks use something similar to MATLAB's stem function. The problem is that stem uses unfilled circle, but our textbook, for example, use filled circles. And I emphasize that this vertical line does not mean. It's just to show which point corresponds to which time index. Okay, so as you've done in the homework, some discrete time signals is better illustrated by using simple plot function. Got it? By the way, when we define a discrete time signal or discrete parameter signal as a function from Z into R or C, there are three kind of singular points we need to take care of. First one is the time origin 0. And it is sometimes natural to define index n equals 0 from the problem we handle. So it's obviously and unanimously defined. However, sometimes we have to set some specific index 0 for convenience of our problem solving. Got it? So usually it's chosen just for convenience. And the others are positive and negative infinity. And in most of the engineering, they just mean very large time index or very small time index or very far away future or very far away past. Got it? So don't be too, rigorous in dealing with these positive and negative infinity. One of the reasons why is that before, most of the digital or discrete time systems had very small number of memory components. So it could just store some of the past data or some of the possible future estimate of the data. And there are many samples goes in and out. So in that era, it was very convenient to use a discrete time signal as a function from Z into R or C. And we may say that far away past and far away future as plus minus infinity or positive negative infinities. Now, as all of you know, the memory components are very inexpensive. And very large memory component is available. Of course, you sometimes have to pay more than $10,000 or $20,000 or $100,000 in some cases. However, if your business or your enterprise will generate more than the price of the memory components, then probably your investors will readily purchase you very expensive ones. So now it could store millions, trillions, and more past samples, data samples. In that case, we just need to handle that data as a finite size vector. So some people boldly say that we don't need to teach discrete time signal process. We just need to teach a vector signal process. So we have a finite vector comes into the system and finite length vector goes out of the system. Then it seems that linear algebra is what we need. We may no longer need techniques related to handle discrete time or discrete parameter signals, which are sequences. Such tools include Z-transform, and many of you hate them, right? And discrete time Fourier transform. Some people just say that, forget about that. Just teach linear algebra. Let's talk about more of Topliss matrices, Hermitian symmetric matrices, eigen decomposition, singular value decomposition, something like that, numerical linear algebra. They are half true. I'm not saying that they are wrong. Okay. So in addition to learning about this classical theory on discrete time signal processing, electrical and computer engineers must also be well equipped with the knowledge on linear algebra. Got it? Anyway, the key of this course is what? Discrete time processing of continuous time signal. So last time we've seen something like this. Digital signal processing is more flexible. Computational complexity is much lower. Speed is much faster. Precision is much higher than analog signal processing or analog signal processors, something like that. So you vaguely already know that this overview already includes those parts. Okay. So here, after we define what is a discrete Fourier transform, and we study, of course, first its fast algorithm called FFT, and then we learn many applications of DFT. And most of the important applications of DFT is what? Is, for example, approximate continuous time Fourier transform, continuous time Fourier series, discrete time Fourier transform, and discrete time Fourier series. So basically, this DFT can be used to do almost every frequency domain and time domain filtering for continuous time and discrete time signals and systems. Once we convert continuous time signal to a discrete time signal. So there are many ways to do that, to convert continuous time or analog or real world signals to a digital or mathematically modeled discrete time signal. There are many, but one that is important in this course and most of the undergraduate courses is the technique to use so-called analog to digital converters. And when, of course, there are many different analog to digital converters, but we focus on the specific analog to digital converter, which consists of these three. The first one is uniform sampler. Second one is scalar quantizer. And third one is binary encoder. So from this one, considering the complement set of this one, you may understand what kind of different approaches could be done. For example, non-uniform sampling is possible. Vector quantization is possible. And non-binary encoding is also possible. And there are many advanced theories specific for handling signals that has some structures. Anyway, so I'm kind of still giving you an overview or just the entire holistic view of this digital signal processing. But we will quickly focus on very, very small pieces and think about details. So here goes the signals and systems review, especially for digital signals. So first, we will see some basic signals or fundamental signals. Or kind of atom-like signals. So every molecule consists of how many? 108 elements, right? So we will see some important signals. And by using these signals, we will learn how to decompose an arbitrary signal. Some basic signals are easy to handle in rewrite a given discrete time signal. But not all of them are always useful. So some specific signal set is useful for some specific applications. And you yourself as a researcher, possibly in the future in the PhD course, may invent your own some signal set that is very, very useful for your purpose. I don't know. Among them, delayed delta functions are very basic and interesting, and it kind of motivates the impulse response concept for linear systems and linear time invariant systems. So we will quickly see that. Got it? By the way, most of you or half of you have seen homework 3, and you may say that, hey, just 2 days. But after you open, you found that the homework 2 and 3 are actually almost the same thing. And in order to tease you, I've given you some final problem like, okay, here goes something like stock market investment and which strategy is better and blah, blah, blah. So enjoy homework 3. Okay, here goes some basic discrete time signals, or you may say sequences, mathematically speaking. So this is called unit sample or discrete time delta function. And it's denoted by a delta of n. Okay, so this function has value 1 if its argument is 0. Otherwise, the value is 0. Got it? Be careful. As I told you, in our handling discrete time signals, arguments can only be integers. Got it? So rational number, that is impossible. Okay? But sometimes, in order to frustrate you, I will give some strange problems, examples like this. Okay, like, okay, here is a function, and illustrate this function. So anybody? So let's say this is n. Okay. So at n equals 0, what is the value? What is the value? By the way, this is the floating or floor function. So 0 divided by 5 is 0, if float is 0, so it's 1. Right? Now at time index 1, again, 1/5. Sorry. At 5, it becomes 1. Right? So argument becomes 1. So you have 0, 0, dot, dot, dot. And similarly, you have -1, -2, dot, dot. Got it? So here, this n is an integer as a discrete time signal. Got it? Anyway, now here goes the unit step function, u of n. And this has value 1 if argument is greater than or equal to 0 and 0 otherwise. So here, be careful, we have 3 dots. Okay, so we have infinitely many these points. And third one is, for example, real exponential. So for example, this signal is a sub n. Sorry, a to the power of n, and a is real, and in this case must be between 0 and 1. Okay. You all know from high school math, and for example, this one, let me see. Yeah, this is somewhat strange, but probably sine some omega n plus theta. Okay. As we see, at n equals 0, we have some non-zero value, means we have some non-zero theta. Another one is that even though it looks periodic, but it seems that there is no value like this. So it's highly likely that this omega is not something like this. Okay. If omega is a rational multiple of 2 pi, then we always have periodicity, but it seems not. Okay. But from this, it's not easy because it may be periodic with very large period. Ready? And some of you barely remember what I'm saying. Okay, so let me give you a simple problem. So suppose you have a continuous time signal, sine omega t plus theta. And here omega is positive and theta is between 0 and 2 pi. And let me ask you a question. Is x of t a periodic signal? Is x of t is a periodic signal? And your answer is yes. Why? Because definition of periodicity is that if x of t equals x of t plus some capital T, positive for all t, then it's periodic and period with t. The problem is that sine omega n, for example, sine 3n as x of n, is it periodic? No, because it is evaluated at every multiple of 3, which is not a multiple of 2 pi. It's non-periodic signal. Okay, be careful. For this argument, if you have no idea, you are not prepared to take this course. Okay, so in that case, just study, review the signal systems again. Anyway, unit sample or discrete time delta function is very, very useful after we delay or advance it. For example, this is delta of n, and let me ask you, what is delta of n minus 1? Since we need to find the time index n that makes the argument 0, at n equals 1, we have value 0 and all others, right? So by replacing the argument n with n minus 1, in the graph, we shift to the right the delta function. What does that mean? If time index n means time, before we shift at time 0, the value is 1. But for example, in 5 seconds in the discrete time domain, which corresponds to the discrete time index 1, we have value. So this is called delay, okay? Delay by unit. Delayed by unit time. Okay, got it? And we may generalize this one for some capital N. If n is positive, the graph shifts to the right, or given the axis, you still say graph shifts to the right. If n is negative, graph shifts to the left. Got it? And you may say that, so what's the use of it? But here goes very interesting thing. Suppose you have P of n whose graph looks like that, and I will ask you, rewrite P of n by using delayed and weighted sum of delta functions. And assuming all the other values not shown in this figure is 0, you find non-zero values of the function and apply that idea of delayed discrete time delta or unit sample. So what is this one? This one is, as it says, A7 times delta of n minus 7. What is this one? A2 times delta of n minus 2. And this one, A1, this one, A2. Got it? Now, what about general, very general function x? And in the first look, it's very strange. We want to rewrite x as here. We have rewritten P as a summation of weighted and delayed delta functions. we want to rewrite arbitrary signal x that is given to you by using delayed and weighted sum of delta functions. And if you look at the right-hand side, it's very confusing. And I also, when I was first met this one in signal gen systems. But let's slow down and find what is the left-hand side. Left-hand side is a discrete time signal parameterized by n. So n is the time index. Now, keeping in mind, see the right-hand side. Even though it has sigma and some summand, which is a product, is this a function of n? No. So this is the function of n. And if you rewrite this one as, for example, for k equals 0, then you have this one. And for k equals 1, you have that, dot, dot, dot. And for k equals -1, you have this one, dot, 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 plus, plus, plus. What does that mean? This formidable looking summation is actually can be expanded by countably infinite terms summation, and each one is what? Weighted and delayed in the time domain with index n, the delta functions. So similar to this example, we can rewrite arbitrary signal x of n using what? Delayed and weighted unit impulse signals for delta functions. Got it? Be careful. This is a function of n, and we have chosen arbitrary summation variable here, k. You may choose L, M, anything other than n, right? So be careful. Anyway, and you may say that this is a piece of k, but this is very giant leap. So it's another small step, okay? It looks like a small step for digital signal processing, but it's a giant leap for electrical and computer engineers. And I will talk about that later. And now let's rewrite the previous elementary and basic function, unit step sequence of function by using delayed and weighted impulse signals. So what can we do? And here, all the signal values are 0. And here, all the signal values 1, 4, and so actually k positive. So here, this summation for this one becomes what? Summation k from 0 to infinity, 1 times delta of n minus k. Got it? So we have this. Sorry, not this one. What is this? Oh, okay. And after change of variable, we can rewrite like that. Is it? Yeah, yeah, I think so. So this is same as that one. And you may wonder, is it really? But just plug in n less than 0. What happens? For k negative, it's all zeros, right? And at n0, it becomes 1. So whenever you have confusion, just plug in, as you've done in elementary school student. And the equivalence of these two can be easily explained after we study the convolution. Anyway, so here goes what I've written, okay? And similar to what you've done in high school math to compute the general term from the its summation series by subtracting the signal u of n and its delayed version, you can get the delta function. Okay? It's not that difficult. And here goes the exponential sequence. And as I told you, if a is positive and less than 1, you have the graph. Looks like that. And sometimes our base alpha is not just your base of the exponential function is not limited to real number. So, for example, you have x of n equals some complex number c to the n, and your complex number can be rewritten as its modulus times e to the j theta, radian angle. In that case, if you plug in here, then you have r to the n and e to the j theta n. Okay, so this is the way to rewrite any exponential functions, especially for real exponential. You will find that you have not only one terms, but also two terms of these things. So the link between the complex exponential and real exponential is what? The Euler's identity. So by using this identity, you can easily convert back and forth from the real exponential and complex exponential. Anyway, sinusoidal signals, as I told you, just can be done. And by the way, from this one, you can rewrite cosine theta as e to the j theta plus e to the negative j theta divided by 2, and sine theta as e to the j theta minus e to the negative j theta divided by 2j. By the way, I prefer using j to denote the square root of -1 instead of I. Okay, so if you are familiar with using I as the square root of -1, I'm sorry. Okay. Okay. Yeah. So simple. I will skip that. Okay. Oh, by the way, I cannot skip. By the way, so you have some exponential signal, but limited to n non-negative. In that case, you may multiply the exponential signal and the unit step function to cut out the negative part. So just to try to visualize the signal and use basic knowledge. Okay. Okay. So the note reviews the notion of periodicity, and the periodicity of a continuous parameter signal and discrete parameter signal is a little bit different. Okay. So let me first talk about periodic or periodicity for continuous time signal. A continuous time signal x of t is periodic if, by the way, if you have a statement for definition, this if means that if and only if. Okay, and many of you who are well trained in your high school math club or in some math courses in your undergraduate courses, you may say that it's obvious, but I myself noticed this fact, simple fact, when I became a graduate student. Okay, so some of you must know this fact. Okay, so a continuous time signal x of t is periodic, or is called a periodic function if what? If there exists t positive, of course real, okay, such that x of t equals x of t plus capital T for all t in R. Okay? Of course, you may generalize to make negative real number can be periodic, but don't do that. Okay, it confuses a lot of people. When people say periodicity and period, they mean some positive number. Of course, here where t is called a period. By the way, we Koreans use Korean language, and it does not have articles, and that makes a lot of problem. Here, you may say that this single letter or character may not mean much, but actually it implies a lot. If I say T is called a period, what does that mean? There could be non-unique periods given a periodic signal. For example, if T is period, T is a period, then you can easily show that 2T is a period. 3T is a period. Any positive integer multiple of period is a period. Got it? Okay. By the way, our theorem also carefully states that a signal, continuous time signal, may not have period. And you may say, it's obvious, right? For example, if x of t equals t, is it periodic? No, you cannot find a positive real number that makes this property for all t. Got it? Another problem is this one. We want to define so-called the fundamental period. So we want to define the fundamental period of a periodic function as what? Is defined as the smallest period. So, for example, let's consider sine 2 pi t. And we know that any natural number serves as period, right? Because if you replace this t with t plus 1, then from the property of sine function, you can show that the x of t equals x of t plus capital T. So it seems that given this periodic signal, you have the fundamental period 1, right? The problem is that some periodic signals does not have the fundamental period. And of course, that is very rare. And in order to make that happen, we have to consider very strange function, such as this one. So this signal x is strange 1. So first, let's define the values of this one. Okay. Values of this function inside this interval. So if t, this is just for fun. It's not that important in this course. Okay. If t is rational and inside this one, the value is 0. If t is irrational and between 0 and 1 is 1. So in almost every point except the countably many rational numbers, it's 1. And now this is repeated. Now, is it true? Just a sec. No, I'd rather do this. Okay. I will just skip this. Okay. So we've defined like this. Now, for other interval, we do the same thing. So in all irrationals, the value is 1. In all rationals, value is 0. Now, let me ask you a question. 1 over n, where n is a natural number, is a period. So let's see. So n equals 1. At 0, if you add integers, it becomes 1, 2, 3, all the integers, and it's 0, right? At 1 or 0.5, same thing, right? Got it? Now, for some strange irrational number, like some 1 over square root 2, if you add 1, what happens? Is it rational or irrational? This is rational, and that is irrational. If you add, it becomes irrational, right? So the value is 1. If you add 2 over n, still irrational. So what you can easily see is that this 1 over n for any natural n is a period of this signal. And if you increase n, the period reduces, right? And there is no smallest period. Anyway, the reason why I emphasize this is, even though it's not important, is that some textbooks, even the textbooks used in the university, says that fundamental period exists. It's not. Okay. Anyway, so here the lessons is that whenever you define something, think about two things. Does it exist? So existence. And when it exists, is it unique? If you are well trained in this procedure, then you are much better than 99.999% of other Koreans. Got it? Because we Koreans have a serious problem in thinking about this. For example, in some debate, I remember, was it some Friday night debate, political debate, broadcast by Munhwa Broadcast Company. And this party and that party members are coming together and just they want to humiliate the other party people in front of the audience. That's the purpose, right? They just forget about persuading them. But sometimes you've already seen this one, right? These guys suggest some solution A, and these guys provide solution B, and they say that their solution is the unique solution to some economic situation of South Korea. There is no unique solution, especially in economic problem. Some of you have taken the introduction to economy, and usually at the end of the chapters, it includes what? Multi-criterion optimization, and talks about some Pareto optimal points. So whenever you have more than 2 objective functions or 2 utilities, then what happens? Even the solution exists, the solutions form some solution set. And if this is one criterion and this is the other criterion, what usually happens? You have uncountably infinite solution points. So from the theory of mathematics, in political situation, because in Korea, how many objective exists? 50 million, because we have 50 million population, right? 50 million people has different interest, and these guys say that they have unique solution. So once I really supported Lee Jun-suk's idea, like we have to enforce exam to every candidate for political position. But anyway, I really hate that guy these days. Anyway, so think about existence and uniqueness whenever you define something. Then you can think much clearer than most of the Koreans and even most of the people in the world. Okay, anyway. And here goes some simple thing, some example. Suppose you have a family of continuous time signals. Actually, this is called complex sinusoidal signal. And here, omega is any real number. And this signal is always periodic. Even in the case where omega is 0. Why? If omega is 0, this exponent is 0 and value is 1. And any constant function is periodic. Any real positive number can serve as period. Of course, it does not have fundamental period, right? Got it? Now, let's move to a discrete time signal. We ask the same question. Is this signal a periodic signal? And as I told you, it is usually not. And it requires that this omega needs to be 2 pi times a rational number in order to be periodic. Got it? And another one is that a constant function, a discrete time signal constant function has the fundamental period, which is 1. Okay? So suppose you have property like this, right? X is periodic with period 1 by definition. What does that mean? X0 equals X1 equals X2 equals X3 equals X negative 1 negative 2. So it's constant. Got it? So a discrete time constant function has the fundamental period, which is 1. However, a constant function, a continuous time constant function, does not have the fundamental period. Got it? Anyway. So here goes some examples which are very simple and easy. And here goes something interesting. So now let's go back to the case where x sub k n is defined this way. So we have many different, apparently different signals by changing k for any integer. Okay, so k is an integer. So x0 of n is a discrete time signal which is all 1, right? What is x1? Something like this. Sorry. What is x2? Something like this. What is xn? And here goes something interesting. See that? This n and n cancels. And you have what? E to the j 2 pi n, which is 1 for all n. So apparently this one with k equals 0, and this one with k equals capital N looks different, but they are the same. So let me kind of briefly summarize this part. In order for a complex sinusoidal discrete time signal to be periodic, its radian frequency. This is called radian frequency, or simply frequency in radian, okay? Must be a rational multiple of 2 pi. And interestingly, if you fix this denominator and change the numerator, you don't have countably infinite signals. You have what? This one, same as that one, and same as that one, dot, dot, dot. And this one is same as x sub n plus 1 of n, and something like that. So even though you have a common 2 pi over capital N, and then you change the frequency, the signals do not that differ. You have at most n distinguishable frequencies. So frequency, for example, 2 pi over 5 is actually same as what? 2 pi over what? 6? 2 pi over 11? Because this is 2 pi times 1, right? This is 2 pi over 5, but actually is 2 pi over 5 times 1. And you add this 5, then these apparently looking different signals are the same. So let me write. Got it? They are the same signals. This is significantly different from the continuous time case. So for example, this is x. Suppose you have continuous time signals, 2 pi over 5t, e to the j 2 pi over 5, 6t, e to the j 2 pi 11 divided by 5t, defined for all t. They are not the same function. Okay? Just plot the real part. The frequency becomes larger and larger. And as I told you, this is review. Now, let's move to the review for discrete time systems. Here goes the definition. And usually, we love to use a block diagram. Block diagram means that we have a block and input arrow and output arrow. For signal gen systems and undergraduate courses, usually we have a single input, single output. However, if you go graduate courses, you may have multiple inputs and multiple outputs. And each one is, in this case, a discrete time signal. So x1 of n, x2 of n, xm of n, y1 of n, y2 of n, yn of n. Okay. And for convenience, sometimes we just write this way. Here, of course, different people, different societies use different notation, but I love this underline or underscore to denote its vector value. Okay? So this entire thing is replaced by that one. This entire thing replaced by that one. Some people love to use double line arrows in order to denote this signal is a vector valued signal. And this is vector value, sometimes triple lines, okay? But, well, this is enough, I believe. So, as I told you, this could be generalized, but forget about these things in this digital signal processing. And let's focus on this simple thing. So you have a single block and two arrows, and you label each arrow with a discrete time signal. And this signal x of n is called the input signal to this discrete time system. And that signal is called the output signal of this discrete time system. Got it? And now, this system does what? It may do nothing. It may just toss input to output. In that case, the relation between the input signal and output signal would be this one. Be careful here, I intentionally have written this one. This relation holds for all n. Such a system is called what? The identity system. Of course, in this case, discrete time identity system. And this mapping rule T may be different, like output is a delayed version by unit time. Of course, we may introduce twice the unit delay, 3 times, and even we mathematically advance it. And you may say that, hey, it's not possible. We may not, see that? We may not generate the output without observing time n plus 1, right? Sometimes this is still okay because, as I told you, the time origin at the output is chosen differently from time origin at the input. Sometimes, got it? Sometimes we intentionally choose different physical time instance so that this time advancement may make sense in the real world. So as I told you, the time origin is chosen most of the times for convenience. So this time advance really means some future prediction in some cases. However, in most of the cases, it's not. So don't be bothered too much unless you are applying this theory to digital control. In digital control, you need strict causality. You need not to confuse yourself by choosing different time origins in different at different system. Never do that, okay? But anyway, and of course, there are some systems like you have continuous time input and discrete time output, and also you have discrete time input but continuous time output, and of course, continuous time input, continuous time output. And we called in signal systems such a system with continuous time in, continuous time out as what? Continuous time system. So this is called continuous time system. This is called a discrete time system. And what are these, by the way? There are many different names, okay? And there is no single word. But we study in this course two specific systems like this, called what? Called uniform sampling. Okay? So we will learn in this course, we will study a special continuous time in, discrete time output system called uniform sampling. I'm not claiming that every system that has continuous time in and discrete time out is a uniform sampler. I'm not claiming, okay? Among many systems, in this course, we study uniform sampler, that has continuous time signal in and discrete time signal out. Similarly, in this course, we will study interpolator, a strange system with discrete time signal in and continuous time signal out in this course. Okay? So our focus is not just limited to discrete time system, but these 4 types of systems, but this is mostly covered in signals and systems. This is half covered in signals and systems, and the rest covered in this course. And these 2, there are many possible systems, but 2 important systems are covered in this course. One is called uniform sampler. The other is the interpolator. Anyway, so here goes examples of discrete time systems. Usually, we label the output as y and input as x, but it's not necessary. Okay, so be careful. But however, if I do not say anything, this is input and that is output. And this is called the input-output relation. And let me ask you a question. How many scalar equals scalar equality do we have here? Just one? Wrong. Countably infinite. So this relation holds for every integer n. So we have what? We have actually, this is a simple abbreviation of what? y0 equals x0 minus nd, y1 equals x1 minus n sub d, y2 equals x2 minus n sub d, dot, 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 and y negative 1 equals x negative 1 minus n sub d, and dot, dot, dot. So how many? 1, 2, 3, 4, 5, 6, 7, countably infinite. Got it? So we have countably infinite scalar equals scalar equality here to define the input-output relation. And as I told you, if n sub d is negative, it's called ideal advanced system, time advanced system. Got it? And as I told you, don't be bothered too much about the causality unless you are applying this to digital control. Now, here goes the important thing, moving average. By the way, moving average is abbreviated by MA. So after you take this course, you will see something like this. ARMA, ARIMA. Okay. And whenever you see this, this MA means moving average. Got it? And also, when you do stock market investing, you will see something like this, SMA. SMA is a terminology for RF engineers for specific type of RF connectors, but not here, okay? SMA is called simple moving average. Then what is not simple for stock market investors? Exponential moving average or exponentially weighted average. Some people say EMA or EWA, okay? This is called exponentially weighted average, but some people love exponential moving average, okay? And probably some of you have already seen strange voodoo type myths saying that if you look at the Samsung Electronics stock price, that is around 60,000 Korean won, and they say that if your 30-day moving average and 180-day moving average crosses and it goes down some value, then suddenly it's time to buy. I really hate that idea. But when they say, they are talking about this moving average. Okay? And in Korean, it is called 이평선. Why it is 이평선? It's abbreviation of 이동 평균선. Anyway, so it's moving 이동 average 평균. Got it? And when the stock market guys are applying this input-output relation, what they usually do is that they find the current value by using past values only, because they cannot predict. For example, suppose you can predict tomorrow's Samsung Electronics stock market price at the end, around at time this. Okay, at 3:30 our stock market closes. Okay, what would you do? Suppose you know the Samsung Electronics stock market price, and suppose it's 2001 higher than today's price. What are you going to do? And if you know, I will collect every my spirit, it's called Youngkel, and buy Samsung Electronics stock, right? And definitely I earn money. That's not possible. But anyway, so what they do is that, because this positive k means that at time n, positive k means past value. Suppose M1 and M2 are positive numbers in their 30-day moving average. What do? The output of their system collects what? 30-day of the past values. See that? Let's say time 0 is the current time. Okay? Then current output. So today, what is the past 30 days average? See that? Since n is 0, x of -1 is yesterday's price. -2 is the day before yesterday. So this is the 30-day moving average for today's, for example, Samsung stock market. Because today, right now the market is still open, so it varies. So usually when they say 30-day moving average, they take 30-day prior to today. Got it? So you see, this is 30, and the upper limit must be 30, and lower limit must be 1 for 30-day moving average. And when I first heard that these stock market guys talks about that myth, like some moving average crosses the other moving average, then it's time to buy, and if the other happens, it's time to sell. It was quite strange. Why this specific number makes that sense? Why not 29 and why not 31, right? So I just decided not to believe what they talk. The problem is that amazingly, that voodoo religion type some theory works in many cases. Why? Because many people believe that. Anyway, so probably in your fourth homework, you will draw these moving average lines on your graph. Got it? So I've provided you some data taken from Cosby, and you are generating these things. Okay. Important properties of systems. So we have a discrete time system. And there are too many different mapping rules between input and output signal. By the way, be careful. Even though I just write here x of n, actually I punch in the entire sequence. And I get entire sequence out. Okay? So it's not like y of n is affected by x of n with the same time index. Okay? I'm not saying that. Got it? So mathematically speaking, this mapping rule accepts a sequence, the entire signal, and generates the entire signal. Got it? And given that, first, what is the definition of memoryless system? Memory means that your output, your current output at time n0 is not a function of xn where n not equal to n0. The trouble of many books, not all, on signal gen systems and discrete time signal processing, they say that this is wrong definition. Y of n is a function of xn for n equals n0 for all n. It looks they are the same thing, but actually not. Let me give you an example. Suppose you have something like this. So this system gives you an output that is kind of modulated version of the input. Now, at time n0, not only x n0, but also e to the j omega n0 affects the output, right? Is it a system, memoryless system or not? This is memoryless. Now, another one. Suppose you have something like this one. So, current output is a squared value, assuming real, value of the current input. Is it memoryless? Yes. What I'm saying is that not only this type of thing, but also that type of discrete time system is memoryless. Because what I'm saying is that this is not dependent upon the past and future values, only current values of the input. Got it? And about linear system, time invariant system, most of you who took signal gen systems already know, but I need to review this probably this Thursday. Okay. And about causality and stability, also I will cover that, okay, because time's almost up today. But anyway, let me give you other examples of memory systems. As I told you, this is wrong definition, and this is correct definition, right? So this one, similar to the previous one, here, cosine 2 pi f0, n is multiplied to the input and output is determined. This is definitely memoryless system, right? And here, this is also memoryless. And what about moving average? Is moving average memoryless or not? In general, it's not memoryless. It's a system with memory, because in order to satisfy this definition of that one, only this type of identity system as a very special moving average can be memoryless. All the other moving average depends, the current output depends on past value or values or future value or values. As I told you, in the real world, we usually use causal, which means that causal moving average, or sometimes just simple moving average. We use past M2 values here by taking this as k from 1 to some M2, x of n minus k. Got it? And we have M2. So this is M2. If unit time means day, M sub 2 day moving average. So if M2 is 30, you have 30-day moving average. It's 120 day moving average. Okay, time's up, I believe, and let me finish.